morning, everyone. Hope we're all bright-eyed and bushy-tailed. We're going to finish off section 3.1 today, get started on 3.2. We've done a lot of practice. There's still more to do on finding derivatives of exponentials and so on, but we're going to use those derivatives to find equation of tangent lines and equations of normal lines. We're also going to look into the idea that you can find a thing called a second, even a third derivative. And we're going to do some velocity acceleration questions and some applications at the end. So quite a mixed bag, really. So let's find a question for finding tangent in normal lines. So let's see, I can see one here. Okay. Here is a version of that type of question. 17 is an example. So I've got a function. It's x to the 4 plus 3e to the x. And we're interested in the equation of a tangent line and a normal line at the point 0, 3. So this thing's slightly out. Still out. There. Well, first thing you do is you find the derivative. I'm going to use y dash notation for that. Power rule, multiplied by the power, reduce the power by 1. And if you differentiate 3e to the x, you get 3e to the x. The x coordinate of this point is 0. So to find the slope of the tangent line, we just evaluate the derivative at 0. So that's 4 lots of 0 cubed plus 3 times e to the 0. Well, that's nothing. And that e to the 0 is 1, and 3 times 1 gets me 3. So the guy that we've got there is 3. And then we use what's called the point slope equation. And this guy here is now going to be called x1, y1. And this is y, take away the y coordinate of p. Take the slope, which also happens to be 3. X, take away the x coordinate of p. Distribute the 3. And then finally add 3 to both sides. And that is the equation of the tangent line. Now we're also going to be asked to find the equation of the normal line through this point. And to get the slope of the normal line, you use the slope of the tangent line. And since the slope of the tangent line here is 3, the normal line is going to be negative a third. And basically, if that one's 7, this is negative a seventh. If that's 2/5, this is negative 5/2. So to get the slope of a normal line, it's negative the reciprocal of the tangent line. So if you think about how I got that negative a third, the tangent line was 3. We'll call it 3 over 1. If you take its reciprocal and make it negative, that's where that came from. Now, apart from that, you use the same equation, the point slope equation. Except now, the slope is negative a third. Distribute the negative a third. And add 3. And we call that the equation of a normal line. What that might look like. If you imagine that point there is 0, 3. Your curve's going through something like that. The green line would be your tangent line, and at right angles to it, the red line would be your normal line. So they tend to, when they meet up, they tend to make a perfect cross. You know, if the blue line's the tangent, you see that the red line kind of follows it. So as long as you know how to find the derivative and then evaluate it at the x coordinate of the point they give you, you will get the slope of the tangent line. And then you use the point slope equation to get the equation of the tangent line. And the same thing for the normal. You just use this guy that you found and use it to get the slope of the normal line. And it's the reciprocal of this, and then you make it a negative. Are we good with that idea? Okay, so I won't give you any more because I believe I gave you one yesterday. So let's look at finding first, second, third derivatives. So suppose I have a function f of x and it's 3x to the 4 plus 2x plus e to the x. I'll make it 3e to the x. It's more interesting. Now we know how to find its derivative. Power rule. 2x gives me 2, and that guy gives me 3e to the x. Well, once you got the idea that you can take a function and do this thing called finding its derivative, you've now got a new function. So it's not unreasonable to assume that you should be able to differentiate that. And we call that a second derivative. And you see the notation? Oops. Use 2 little dashes inside A1. And what does the second derivative look like? It's, you differentiate this guy, the first derivative. So it's another power rule. That gets you 0, and you get 3e to the x. Now, if you can do a first derivative, which is what that one is, that's its full title, we normally just call it the derivative. You can get a second derivative, but there's no real stopping to this. You could then do the whole thing again and get the third, the fourth, the 55th. You could keep doing it until you get bored. So we're comfortable with what a second derivative is. It's just the derivative of the first derivative. And a third derivative would be the derivative of this. In fact, I'm not doing it. If I did a fourth one, it would be 72 plus 3 to the x. Are we good with that? Let's do an example. Question 19.
I have a question actually.
Yes.
What is the point of doing multiple derivatives? What is it used for?
That is cool. There are going to be two main uses for finding, say, second derivatives in particular. The first one is that we can use it in applications. So if you hold off for 5 minutes, we'll tell you what that is. And the second usage you'll get is later on when we use derivatives to tell us about the shape of a curve. So the first derivative kind of tells you how the curve is sloping at any given point. And the second derivative tells us a thing called curvature. And curvature means that's an example of positive curvature, right? When a shape is making a kind of happy face. And that's an example of negative curvature. And that's when a shape is kind of making sad faces. And the second derivative tells us what kind of curvature is going on in a curve. So if you had a curve and you knew what its second derivative is, you'd be able to say at that point and close to that point, the shape looks like a happy face. So what the second derivative does is it tells you a little bit about the shape of a curve. And the other usage is for velocities and accelerations. So let's do this one, and I'll actually show you the second derivative being used right after that. So we have 3x take away 4x to the 5, 6. So the first derivative, power rule. This one's messy, but if you multiply this by 5, 6, and then you take 1 away, you get that. And 20 over 6 is the same as 10/3. And then you do the second derivative. We'll differentiate that, you get nothing. Differentiate this, 2 negatives make it a plus, and you get 10 over 18, which is 5/9. And then you subtract 1 to get 7, 6. Now, still points. Since the original question had fractional powers, have you noticed that these two answers also have fractional powers, right? Rule 1, make it look like the original. So in fact, in those questions, I didn't have any style points at all. They need to change it. So this is how you calculate second and so on derivatives. You just differentiate the first derivative to get the second, and you differentiate the second derivative to get the third. So let's look at finding velocity and acceleration. Now, before we get into this, a little bit of physics, very bad physics, because that's not my thing. Velocity is the rate of change of the position of an object with time. Basically, the difference in position divided by the difference in time. S is very common, the position function. So here is the position of an object at time t, and it's given by this quite long polynomial. Now, if I want to find the velocity, in other words, how fast is this object moving at any given value of t, all I need to do is find the rate of change of this function, which we call that the first derivative. So 4t cubed, take away 9t squared, take away 2t, take away 1. So there is a very interesting property of the first derivative. The first derivative of a position function actually tells you the velocity of that function, how fast it's going at the 1 second mark, at the 10 second mark. Now, for your second derivative, isn't acceleration the rate of change of velocity with time? Which means that if you want to find the acceleration, you differentiate the velocity function. Well, since the velocity function is itself the derivative of the position function, can you see that the second derivative tells you acceleration? That's very powerful. If all I know is where an object is at any given time, then by differentiating it once, I can tell you its velocity at any given time. And then by differentiating a second time, I can now tell you what the acceleration is. Let's find out the acceleration. Power rule, 12t squared minus 18t take away 2. Now, velocity and acceleration of a moving object are very important things, right? They're things you want to know. They tell you a lot about how the thing's moving and how it's going to change its movement over time. I guess the natural thing to say is, what would be the third derivative. I mean, I could do it, right? Well, if I find the third derivative, it's, in this case, it's 24t take away 18. And you can look this up, because I thought students were telling me something that's wrong. That's actually called the jerk. So if any of you are into mechanics, evidently there's a property of a moving object called the jerk, which is essentially the rate of change of acceleration. So I'm not sure what that is, so I'll make it up. But if you were in a really fast moving object and then somebody like put the turbo on and it became even faster moving object, there would be a kind of, you know, get that jerking motion. Whoa, I'm going even faster. I think that might be where its name came from. That would be my total made up reason for why it's called that. So finding first and second derivatives are very helpful. If you know the position function, the first derivative is velocity and the second derivative is acceleration. Now, I can't remember who asked that, but have we convinced you that this might be useful to do?
Yeah, it's pretty useful.
So if you're into that kind of thing, there are all sorts of other applications to finding second derivatives. Really, all you're doing is finding rates of change of things. That's what a derivative, one way of looking at a derivative is how it's changing through time. And let's do one more of those. The position of an object is t cubed take away 27t. Its velocity is the derivative of the position function. So it's 3t squared take away 27. And the acceleration is just 6t. And now you can be asked questions like, what's the velocity at the 3-second mark? And you might be asked, what's the acceleration at, say, the 2-second mark? Well, the velocity is this function. So it's 3 lots of 3 squared take away 27, which is 0. Let's say the units are meters per second. Okay, what's happening to this moving object at the 3-second mark? Its velocity is 0. So what could you say about it? What's 0 velocity tell you?
It's not moving.
It's not moving. So for whatever reason, this object is, for an instant moment of time at least, it's stationary. Can you imagine an object that might be shooting to the left, hammers on the brakes, stops for an instant, and then turns around and goes to the right, you know? So, you know, some kind of movement that's quite flexible. Now, 6 times 2 is 12. And if you've ever done any physics, aren't the units meters per second, which are called meters per second squared? So what that is telling me that at the 2-second mark, this object is actually getting faster and faster by 12 meters per second every second. So if I gave you a position function, typically they're called S. If I gave you a position function, do you feel comfortable you could find velocity and acceleration? And you could do it at any given value of t. We feel good about that. Then let's move on. I can start chopping up my little list. There are a couple of application questions. The two questions that are right at the end are 22 and 23. I call them applications. There's really no way for me to, you know, categorize them. They're kind of special. But let's look at 22 then. Someone has found a model where L is the length of an Alaskan rockfish at age A. And evidently, because the person had plenty of time on their hands, they found out it was this guy here. Let me start that again. It's so big, I need more room. And we don't need to know about rockfish or the fact that they grow according to this really weird formula. L is their length in inches and A is their age. And they give you the question, says find the derivative. I haven't used this notation much, but that basically means the derivative of L where A is the variable. And then a vertical line, A equals 10. So to calculate that, first thing I'm going to do is find the derivative. Now, I don't care if you call it Tx or capital A, the derivative is still the derivative. So you multiply by 3. I need a calculator for these. So it's a power rule. 0.155 times 3. So I get 0.465 A squared. Take away. So multiply that by 2 and you get 0.744 A plus, there's a decimal point there, plus 3.95. So that is your derivative. And we're going to evaluate the derivative at A equals 10 years. So this is what a 10-year-old Alaskan rockfish, this would be its length, typically. 0.465 times 10 squared. Take away 0.744 times 10, add 3.95, and that's why we have calculators. So that's going to be 46.5 plus 7.44 plus 3.59. And we would get, or I got that guy. And what were the units? Inches. Per year. Wow. Something doesn't look right.
I think someone was raising their hand and then they turned it off.
I'll check the chat. That number is too big.
I raised my hand because of the first number that you entered with the A to the third. You typed it in as 0.155, not 0.0.
Okay, so there's a 0 missing here. Okay. That will make a nice difference. 4.65, take away 7.44, add 3.95. It shouldn't be that hard to do. And the answer I got here is 1.16 inches per year. And that kind of makes sense, right? A fish growing 57 inches a year would better be a whale, right? It better be some massive. 1.16 inches per year does sound, reasonable, right? And it is one of the choices. And then it says interpret. What does that mean? Well, it means that the rate at which a 10-year-old fish is growing is that in the next year, it's likely to grow about 1.16 inches, right? So when it's a 2-year-old fish, it might grow half an inch. And when it's a 10-year-old fish, it's going to grow about 1 inch a year. It might be one of those really, long-lived fish. So you might be able to say at 30 years old, it might be growing at 2 inches a year, right? So you now kind of know how that fish is going to change, how its length is going to change throughout time. If this, and the fact that they are such ugly numbers makes me think that this is actually not a made up question, but a real question. Because you know, when you do real numbers in real life data, you never get 2x squared plus 4s. It's always nothing 0.123 and weird stuff. So if this is a good model, what that tells me is that if they are interested in Alaskan rockfish, can't you use this to do all sorts of things? Couldn't you, for instance, if you know the length of it, you could have a good idea how old it is. You know, a 12-year-old rockfish is probably 4 years old, but a 15-inch one is 5 years, things like that. And that's cool. After a little hiccup. Now, the last application question goes something like this. Y equals x cubed plus 3x squared, 9x plus 1. Now, I'm not going to draw that
the screen yet, sorry.
accurately, but I can tell you what it's going to look like. Isn't it going to be a cubic?
We can't see the paper.
Could you not see it the previous one? The entire question?
Oh no, we saw the previous one, but when
Oh,
yeah.
don't know what I'm doing. It must have been when I went to see what the chat was saying. Okay, I can't really see the chat when my screen's on. So thank you, Vanessa, for telling me someone had their hands up. Right. From 141, would you agree that when you see an x cubed, they all kind of look like this, right? Now, in question 23, we're being asked to find when the tangent line is horizontal. Now, if my picture is right, which I know it's not, wouldn't you agree that there are 2 places on this curve where the tangent line is a horizontal line? And in fact, doesn't that correspond to the top of this hill and the bottom of that valley, right? So we are going to find the derivative. And it's 3x squared plus 6x take away 9. And since these are horizontal, what number is a tangent when the line is horizontal?
0?
It's 0. So we are going to find, the question asks us to find the x coordinate of those 2 places. So to find the x coordinate of when the tangent line is horizontal, we find when is the derivative 0 and solve. Okay, you got a quadratic here. Anybody want to give us a, as long as you do it to both sides, it might be a good idea to make this quadratic easier to do. I mean, I could do it the way it's written, but I want to make it easier. Anything you can do to that quadratic to solve it in a simpler form.
Add 9.
Oh, like get it all to the other side. Not a good
Yeah.
idea for quadratics. Good idea for almost everything else, but not for quadratics.
Pull out a 3.
I agree. And if you pull out a common factor of 3, you get that. And hopefully we all remember how to factor quadratics. Since this is an x squared, it's a lot easier to do. 2 numbers that multiply together give me -3, but when I add those 2 numbers, I get +2. So clearly one of them is positive and one of them is negative, right? So what is the combination? There's not many to choose from here.
-1 and +3.
Okay, which now tells me that one of the solutions is x equals -3. And the other solution is that this derivative will be 0 at x equals 1. So far, so good. Now, I told you that picture was wrong. You can tell that -3 and 1 aren't there, but that's the real numbers. So what we can now do, it says smallest x. Well, the smallest x is -3. And then the larger x, it's 1. And, oh, they want the y coordinates. Okay. So when x is 1, you go 1 cubed, 3, that's 4, that's 5. Take away 9 is -4. And when it's -3, yikes, you get -27 plus 27. Okay, that's good. 27, 1, you get, I believe, 28. And there you go. So this one was an application where they gave you a formula to do with a rockfish's length, and we found its derivative at a particular point. And this one, we had a question where we were given a cubic and we were being asked essentially to find the places where the tangent line is horizontal. And couldn't I also find the places where the tangent line was 10? Wouldn't that just become solve when is this equal to 10, right? If you want to know when the tangent line is -2, wouldn't you make the derivative equal -2? And in their question, they wanted to know when it was horizontal, so it was 0 we're looking for. But you could do it for any number, right? There's no, right? So if I was interested, where on this curve do I get a slope of 7? You know, it might be here and here, right? Wouldn't I just find the derivative, make it equal to 7 and solve it? And that would be 2 solutions typically. Done. So we are now moving on to 3.2. Is there any questions before I actually do that? Right, so are you okay with if someone gives you a y equals function of x and you want to find when its slope is 0 or 10 or a number, that you know how you're going to do it? Okay. Here's our next guy. We are expanding the things that we can differentiate by using this called the product and the quotient rule. What the product rule allows us to do is to find the derivative of a function y that's written as 2 things multiplied, right? F of x and g of x. And it's a formula, it's a plug and chug formula. It's that guy there. And the quotient rule allows us to find the derivative of a function y, which is basically a fraction, right? An f of x over a g of x. And it's got a much uglier formula. And you really have to memorize these things because you are going to be using them forever. If you keep doing calculus, I can't think of a situation where you're not going to do a product rule or a quotient rule sometimes, right? It's one of those things that just gets used a lot. So let's show you what it looks like. Nice simple one to start. I would like to know the derivative of x cubed e to the x. Right now, you know, if that you didn't know about this, wouldn't this be an impossible question if I asked you 10 minutes ago? I know how to differentiate x cubed. I know how to differentiate e to the x, but I don't know how to differentiate x cubed e to the x, right? And you might say, well, can I just make up a rule like you do this to that guy and, you know, differentiate them separately and multiply the answer and all sorts of things like that? Well, you could make up rules, but they don't work. What rule does work, however, is this one. So f is this guy and g is this guy. And so the derivative, well, let's use that notation. Now, it's written down here as f dash g plus f of g dash. That gets really boring really quickly. So here is the same formula, just abbreviated a little bit. Would you agree that writing that down means the same as that without all those bracket x's? So I'm going to differentiate this fella. You get 3x squared, and this guy is g. And then you leave this guy alone, and you differentiate this guy, who just happens to be e to the x. And there is your derivative. So far, so good. Now you're going to do style points. And in the product rule, and later on you'll see in the quotient rule, there is a lot of algebra involved in making it look good. Style points. Most of the time, your answer is going to be factor the heck out of it, right? So here's the 3 rules again. Number 1, make it look like the original. Well, yeah, it looks like the original. So you're not going to do probably much about that. But number 2, factor the heck out of it. Okay, look at these 2 terms. What common factors can we take out?
X squared times EX.
You take an x squared and an EX, agreed. And if you take it out of this, you're left with 3. And if you take what we just said out of this, you got X. Now you are finished. And the third rule that we haven't used much is if it's a trig function, look for identities to make it pretty. And that is that fella. What else can we do? Try to think one before I look at their questions. We really need to add to our list of functions, but we don't have many functions that we can add to yet. So, okay, I'm just looking at that. Okay, that'll work. This is an example of question 1. And what we have here is 1 plus 3x squared, x, take away x squared. Now, I don't actually need the product rule to do this question. Would you agree I could just FOIL it out and do the power rule? So I'm not really convinced this question is really a good usage of the product rule, but that's how we're going to do it, so we'll look for it. That guy's F, this guy's G. If you want to differentiate it, F dash G plus F of G dashed. Right, differentiate F, you get 6x, leave the other one alone. Add, leave the first function alone, and multiply by the derivative of that guy, which is 1 minus 2x. And now we have style points. Well, I'm going to have to distribute all of this. So that's 6x squared, take away 6x cubed. I'm going to FOIL this out, so I get 1 minus 2x plus 3x squared minus 6x cubed. I got this guy and this guy, so it's negative 6x and negative 6x, that's 12. Again, that guy. I got this one and this one, which looks like it's 9x squared. I have a negative 2x and a plus 1. So that's make it look like the original. There is nothing I can see here that can be made better. If it was a quadratic, I would try and factor it, but not all quadratics factor. And if it's a cubic, especially a cubic with a number at the end, I don't think you're going to factor that anytime soon. Would you agree? They're just not designed to get factored. Now, there are exceptions. Can you imagine that the answer was just those 2 terms? You see those 2 guys there? That's a cubic, but couldn't I pull out x squared or 3x squared as a common factor? And that would be doable, right? So if it was those 2. So when you're looking at style points, for the most part, you're going to be saying, how can I factor this? Right? Is there a possibility even that I can factor it? I don't think that's an advantage. I think if you FOILed this out, wouldn't it be just as much work and you get the exact same answer? So just because you could doesn't really mean you need to do it that way. So yeah.
Is that, sorry, that's a negative 6 cubed plus 3x? Wait, no.
It's
Never mind, I read it wrong.
Okay, you're good? Right. There is not that many examples of the product rule being used in a very efficient way. I'll show you one of theirs. This is question 5. And then the product rule is going to come back with a vengeance, but it won't really help you much until you get to add to your list things like derivatives of trig functions and 2 to the x and lots of other functions. Then the product rule becomes useful because you're going to mix and match different things. But right now, isn't the only thing we got is polynomials and e to the x, right? So there are not many ways to match those things, right? You can have a polynomial with an e to the x, right? That's it. Or you can have this guy times some other guy. Now, this one does have a little bit of a change. Since I am going to be differentiating, I'm going to call that square root x to the half. This package here is going to be the f, and this little guy here is going to be the g. So the derivative is f dash g plus f of g dashed. If you differentiate this guy, you get 1, and you get multiply by the power and reduce it by 1, and then e to the x. Then you have this guy untouched, and then the derivative of e to the x, who is e to the x. If I pull out e to the x as a common factor right now, I'm going to have this guy plus this guy. And there's really not much I can do to this except make it look like the original. Three x to the negative a half is 3 over 2x to the half, 3 over 2 square roots. 3x to the half is 3 square roots. So I'm making it look like the original. I can't see anything in that list there, and I'm pretty sure there isn't, that you could factor, right? Once you pull out the e to the x, would you get everything else is just what's left over. Are we good with that one? Right, now I'm going to show you an example of a rule that I have made up my name for. You know, like my rule, as long as you do it to both sides, it's okay rule. This rule is called, oops, try that again. Just because you can doesn't mean you should rule. It comes around when I was young, and I used to sing in the shower, still do, drives my wife crazy. And I'm not a good singer, and I don't know half the words, so I make up my own. It's just the way I do things. It's my thing. But when I was really young, my mum used to bang on the door and say, just because you can sing doesn't mean you should. So this is where this rule comes from. I'll show you an example of how it would be used. Suppose you had to differentiate that function. You could do this function with a product rule, right? It's designed that way, right? It's two things multiplied. You could do it as a product rule, but you shouldn't. If you try to do this as a product rule, will you trust me that it will be ugly and long and messy before you finally get your right answer? right? It will work, but not a good way to do it. Sometimes it's just better to do this. X times X is X squared. X times that guy is X square root of X. That guy gets you negative X square root of X. And this guy times this guy gets you negative X. And so you now end up with that guy. And that guy is him. So you want to differentiate him? Wasn't that very easy to differentiate? Now, if you left it like that, wouldn't you be doing an F dash G? So you'd be differentiating that guy multiplied by this guy, plus leave that guy alone times the derivative of that other guy. So aren't you going to have all sorts of x's to the halves and x's to the negative halves all being multiplied and having power rules done to them? And then at the end, you're going to have to FOIL out a whole load of stuff, collect a whole load of stuff, and it's really cool when you see it. Everything dies except these two. Right? Everything gets killed off by something else, and that's what's left. And you look at the answer and say, oh, that was a really nice answer. Took me a long time to get it, but it was a nice answer. Do you see how sometimes a little bit of FOIL might be a better strategy? So don't assume that just because something looks like it's a product rule, that you must do it as a product rule. Give it a chance and see whether or not there is another strategy. So while you're putting down your names for attendance, I will zoom over to the homework and I will try and find you some examples of what I just said. Question 6. You see that guy? Maybe make it bigger. That would be an example of just because you can doesn't mean you should. That's a product rule, right? You can do it as a product rule. Can you trust me that if you FOIL that out, you end up with less work? That's another horrendous product rule. But if you FOIL it out first, right, do a little bit of FOILing, it's much easier to do. You recognize that guy? That's actually the one I did with the U. And then you get kind of to the point where it's just as much work to FOIL it as it is to do the product rule. So I'm not quite convinced that 9 is a just because you can doesn't mean you should question. I think that one's kind of, both are going to be messy, both are going to be ugly. They're both probably going to take you about the same amount of time. So that would be the borderline case. That one's really nice if you do the product, if you do FOIL first, and these two definitely. So there is an example. Now, on the other hand, if you were going to do this guy here, that's what product rules are for, right? That's a classic use of product rule. This piece here would be F, and that little square root guy there would be the G. Similar looking question. Pretty nice question, that one. Have you noticed that almost all of the questions, at least more than half of them, aren't they something to do in X times an e to the X? You see, right now, they're the only two guys we've got to play with. But in a little while, we're going to have, probably tomorrow, we'll definitely do it by Thursday, you're going to be able to add things like X sine X, e to the X cos. Don't do that face, Izzy. You're going to be able to do a lot more multiplications. And so hopefully by that time, you'll see that the product rule is worth it, right? It allows you to do things. And that is us for today. So with